Hello, and welcome to this short presentation on binomial expansions and Pascal's triangle. A binomial expansion is one that contains two terms connected by a plus or a minus sign. For example, x plus y, or p minus q all squared, or a plus x cubed are all binomial expansions, two terms inside the bracket. If we expand a plus x to the power n for integer values, that's n values from 0 to 8 in this case, it produces the result shown in the table below. This is expanding the binomial bracket a plus x to the power n when n is 0 through to n is equal to 8. Don't forget anything to the power of 0 is 1, so a plus x to the power of 0 gives us 1. Anything to the power of 1 is itself, so a plus x to the power of 1 is a plus x. Here we've got a plus x to the power of 2, the binomial bracket expansion. We're used to doing this with a crab claw method or a smiley face method, whichever you prefer. Basically what we get here is a times the a, will give us a squared, and a times the x plus x times the a, which basically gives us plus 2ax, and then plus the x times the x gives us x squared. We're quite used to doing that kind of expansion. If we now consider a plus x cubed here, which is a plus x squared times a plus x, that would give us a cubed plus 3a squared x plus 3ax squared plus x cubed. If we do a plus x to the power of 4 now, that's a plus x cubed times a plus x, again multiplying the brackets out, we get a to the 4 plus 4 times a cubed x plus 6a squared x squared plus 4ax cubed plus x to the 4. We could do these expansions, but they're obviously getting more and more difficult here. We've also shown here a plus x to the power of 5, a plus x to the power of 6, a plus x to the power of 7, and a plus x to the power of 8. And of course they get more and more difficult expansions as we increase the power. Okay, what we're going to do now is look for patterns in the previous expansion of a plus x to the n. And I've repeated some of table 1 here just for convenience, so we've got a few rows of the a plus x to the n from the previous slide. So the first pattern we notice is that a decreases in its power as we move from left to right. So if I take the squared expansion here, so a plus x all squared, what we've got here is a to the power of 2, there's an a to the power of 1 there, we don't write the 1s, but that would be a 1, and we could say there's an a to the power of 0 in front of the x squared, because a to the power of 0 is 1. If I take a power of 4 expansion, I've got a to the 4 on the left hand side, then a to the 3, a to the 2, a to the 1, a to the 0. If I take a power of 6 expansion, I've got a to the 6, a to the 5, a to the 4, a to the 3, a to the 2, a to the 1, and a to the 0. So we can definitely see the power of a decreases as we move from the left hand side to the right hand side of the expansion. Pattern 2 relates to the x, and the x increases in its power as we move from left to right. So if I take the cubic expansion, what we've got here is basically x to the power of 0, because again that's 1. We've got x to the power of 1, don't write the 1s, but the 1 is there, x to the power of 2, x to the power of 3. If I take a fifth expansion, I've got x to the 0, x to the 1, x to the 2, x to the 3, x to the 4, x to the power of 5. If I take a power of 7 expansion, I get x to the 0, x to the 1, x to the 2, x to the 3, x to the 4, x to the 5, x to the 6, x to the power of 7. So again we can clearly see that the x increases in its power as we move from left to right. Okay, looking at patterns again, pattern 3 we notice that when n, the power, is even, the coefficients of each of the terms are symmetrical about the middle coefficient. So let's take a squared, an even power there. What we notice here is that the middle coefficient is 2, and adjacent to that we have a 1 for the a squared and a 1 for the x squared. If we take power of 4, another even expansion here, the middle coefficient is 6, and then symmetrically about that we have a 4 to the left and a 4 to the right, and again a 1 to the left and a 1 to the right. And if I take the power 6 expansion, another even expansion, the middle coefficient is 20, and then either side of that we have a 15 coefficient, and then a 6 coefficient, and then at the extremes we've got the 1 coefficient. When n is odd though, the coefficients are symmetrical about the 2 middle coefficients. So if I now take, for example, cube expansion, it's an odd expansion. In the middle we've got 3 and 3 for coefficients, and either side of those we have a 1 and a 1. If I take a power 5 odd expansion here, in the middle we have 2 10s, and then either side of that now we have a 5 coefficient, and then back to our 1a to the 5 and 1x to the 5. And taking the power 7, the odd expansion here, again the middle 2 terms are 35 for the coefficients here, and then either side of that we have 21, then we have 7, and then the 1s again at the extremes. So we can definitely see that there's symmetry about the 2 middle terms when the power is odd. Okay, patterns continued here. Pattern 4. The coefficients, that's the numbers, are shown separately in the table below. And this arrangement is known as Pascal's triangle. Now a coefficient of a term is obtained by adding 2 adjacent coefficients immediately above in the previous row. So for example, if you look at here, this number 4 here is obtained by adding above, in the previous row, the 1 and the 3. This 15 here is obtained by adding above the adjacent terms in this row of 5 and 10. This 35 coefficient is formed by the 15 and 20 added above. You can see up here the 1 and the 1 adds to give you the 2. So again, another pattern we can see from what's termed Pascal's triangle, just looking at the coefficients only in Pascal's triangle. Patterns continued here. Item 5. Now, the Pascal's triangle method is used for expansions of the form a plus x to the power n, although of course the a and the x can be different variables, but that's the basic format, a plus x to the n, for integer values of n usually less than 8. I've actually shown the expansion of 8 here in the table, but usually it's less than 8. For other expansions, higher expansions, there are other methods we can use. Example 1p here. We're going to use Pascal's triangle to determine the expansion of a plus x to the power of 9. So we know from the previous table we did have an expansion a plus x to the power of 8, and these are the coefficients in Pascal's triangle that we have on that previous slide. Now we need to find the expansion of a plus x to the power of 9. So don't forget the way we can do this from item 5 of our patterns is to add the adjacent coefficients above to get the new coefficient for the expansion to the power 9. So we start with a 1 on the left hand side, then we add 1 to 8 to give us the 9 for the next coefficient, we add 8 to 28 to give us 36 for the next coefficient, 28 to 56 to give us 84 for the next coefficient, 56 add 70, 126 for the next coefficient, 70 add 56, 126 for the next coefficient, and now we'll see a symmetrical pattern evolve. 56 plus 28 gives us 84, 28 plus 8 gives us 36, and 8 plus 1 gives us 9, and we have a 1 at the end. So now we can expand the a plus x to the power 9 using the coefficients for the a plus x to the 9 expansion for Pascal's triangle. So on the left hand side we get a to the power 9, x is to the power 0 there, and we get 9 a to the power 8, x to the power 1, plus 36 a to the power 7, we're decreasing our a values, x to the power 2, we're increasing in our x values, 84 times a to the power 6, x to the power 3, plus 126 a to the power 5, x to the power 4, and so it goes on for the rest of the series there. I'll let you look at the rest of the series. We're using Pascal's triangle we've expanded a very complicated problem of a plus x to the power 9. Example 2p here, we're asked to determine, using Pascal's triangle, the expansion 2q minus 3z all to the power of 5. We know from Pascal's triangle expansion of a plus x to the power n, we've got power 5, the coefficients are 1, 5, 10, 10, 5 and 1, and we know that when a plus x to the power of 5 is expanded, we get 1a to the 5 plus 5 times a to the 4 x to the 1 plus 10 times a cubed x squared plus 10 times a squared x cubed plus 5 times a to the 1 x to the 4 plus x to the 5. What we need to be careful of now is that our expansion is not a plus x in this case, it's 2q minus 3z. So in this case we need to be very careful. The a in our question is actually 2q, and the x in our question is actually, be very careful here, it's minus 3z. You must take the negative with you. It's a negative 3z in our bracket. So all we do now is put the value of a and x into the equation above. So instead of having a to the 5, we would have 2q to the 5. So wherever we see an a now, in that line above, we will put 2q. So that's where the 2q's go. They're replacing the a's. Wherever we have an x now in the above line, we're now going to put minus 3z. So I get a minus 3z here. This is on my 5a to the 4 times x, so that would be times minus 3z here. Wherever we have an x in the above line, we're now going to put minus 3z. On the next line, what I've done is calculated the values of the brackets where I've got powers. You need to be very careful here, because in the first term you have 2q to the power 5. So that means 2 to the power 5 is 32, and then q to the power 5 multiplied against the 32. If you take the next bracket, you have 2q to the power 4, so don't forget that's 2 to the power 4, which is 16 times by q to the power 4. In the next bracket you have 2q cubed, so don't forget 2 cubed is 8, and that's multiplied by the q to the power 3 there. Next bracket I have 2q squared, so that's 4q squared. So be very careful that you expand the brackets correctly, or you raise them to the correct powers here. If I look at the x terms, I have here a minus 3z squared, so that will become positive 9z squared. So minus 3 times a minus 3, positive 9z squared. With this one here, I've got minus 3z cubed, so minus 3 times minus 3 times minus 3, which is cubing it, gives you minus 27z cubed. Next bracket I have minus 3z all to the power 4, so minus 3 times minus 3 times minus 3 times minus 3 gives you plus 81z to the power 4. And the last one I've got minus 3 z all to the power 5, and that will be minus 243, that's the minus 3 to the power 5 times z to the power 5. So just be careful how you raise the values in the brackets to the respective powers. So tidying this up now, on the last line we get 32 times q to the power 5, and then we get 5 times 16 times minus 3 is minus 240 q to the power 4 times by z. The next term we get 10 times 8 times 9, so that gives you plus 720 q to the power 3 z to the power 2. And then the next term we get 10 times 4 times minus 27 is minus 1080 q to the power 2 z to the power 3. And we get 810 q times by z to the power 4, and finally we get the minus 243 z to the power 5. I'll let you check those figures for yourself. Question 1p continued. We're going to use Pascal's triangle here to expand x minus y to the power of 7. We know from previous work on the previous slide, we've got a plus x to the power of 7 gives you expansion on the right hand side here. But don't forget, a plus x is generic terms we're using. In our particular case, our a, generic a, will be x, the question we're given. And the x in our generic expansion will actually be minus y. So x is actually minus y in the question we're given. So we need to be very careful of that. So we now need to put the value of a and x into the above expansion. So on the left hand side, instead of having a to the 7, I will have x to the 7 plus 7a to the 6 times x, it says here, that will be 7x to the 6 times negative y. Plus 21a to the 5 x squared will be plus 21x to the 5 minus y squared. Then plus 35a to the 4 x to the 3 becomes plus 35x to the 4 minus y to the power of 3. And then plus 35a cubed x to the 4 is plus 35x cubed, and the minus y to the power of 4. And so it goes on for the rest of the terms there. Now again, be very careful when you raise the brackets to powers. The first term is fine, that becomes x to the 7. Second term is okay, just be careful that you're multiplying a positive by a negative here, so you get negative 7x to the 6 times y. Now with the third term, we've got 21x to the 5, then it's minus y squared. Don't forget, when you square a number, or a negative variable in this case, you get a positive one. So that minus y squared becomes positive y squared here. When you raise a minus y to the power of 3, you will get minus y cubed. You get a negative again. So minus y times a minus y is a plus y squared, times a minus y is a minus y cubed. When you're looking at the power of 4, when you raise minus y to the power of 4, you get positive y to the 4. So it goes on. Be careful with the other brackets. So when you simplify to get your final solution, you get x to the 7, take away 7x to the 6 times y, plus 21x to the 5 y squared, negative here, change the sign, minus 35x to the 4 y to the cubed, plus 35x to the 3 y to the 4, another change of sign here, minus 21x squared y to the 5 plus 7x y to the 6 minus y to the 7. There's our full expansion. Notice the alternating signs of plus and minus as you go across from left to right. Okay, question 2 here, we're going to use Pascal's triangle again to expand 2p plus 3q all raised to the power of 5. We know from previous work that a plus x to the power of 5 gives you expansion on the right hand side here. Now be careful, in our case the a in our generic expression is 2p, so a is equal to 2p in this particular question, and the x in our generic expression is plus 3q, so x is equal to 3q in this particular case. Be very careful you extract the correct values there. Now we're simply going to put the value of a equals to 2p and the x equal to 3q into the above expression wherever we see the appropriate terms. So on the left hand side here, I've got my a to the 5, so that will now be 2p to the power of 5 because a is 2p, and you must have a bracket here. You must put the 2p in a bracket. If you don't put the 2p in a bracket, you'll have 2p to the 5, and that means the p is raised to the power of 5 and not the 2, and that's wrong because a in this case is 2p and a is raised to the power of 5. So 2p to the 5, 2p in brackets. Plus, the next term we've got is 5 times a to the 4 times x, so that'll be 5 times a again, 2p in brackets to the power of 4 times by x, which is 3q, plus our next term here, 10a cubed x squared, so plus 10 times a, 2p to the power of 3, multiplied by 3q, and that's squared. And then we've got next term is 10a squared x cubed, so plus 10 times a, 2p squared, multiplied by 3q to the power of 3. So it goes on. I'll let you look at the last terms there. On the next line, I'm simply raising the brackets to power. So again, be very careful here. When you raise 2p to the power of 5, you get 32, because 2 to the power of 5 is 32p to the 5. First term, plus 5 times, again, you've got 2p to the 4, so that becomes 2 to the power of 4 is 16p to the 4 times by my 3q, plus 10 times 2p cubed, 2 cubed is 8, so that's 8p cubed, and then be careful, you've got 3q squared, so that will become 9q squared there. Next term you've got 10 times by 2p squared, so that becomes 4p squared, and that's multiplied by 3q cubed, so that becomes 27, 3 cubed, q cubed. I'll let you do the rest of the terms in that line. So for the final solution, we've got 32p to the 5, plus we got 5 times 16 times 3 is 240 p to the 4q, plus we've got 10 times 8 times 9, so that's 720 p cubed q squared, plus 10 times 4 times 27 is 1080 p squared q cubed, plus 10 times 81 is 810 p q to the 4 plus 243 q to the 5. I'll let you check those figures. And here's the reference source used to help develop the presentation, a very good maths book. I suggest you refer to this for further information. I hope this presentation has been of interest to you, and thank you for viewing.